Thanks very much. I'm really excited to give this talk, and I know the name is a little bit intimidating, especially at, 3:30 in the afternoon, but bear with me. I think this is some really interesting and very powerful techniques, and hopefully we'll have some time. Feel free if you want to ask questions during the presentation. Hopefully we'll have some good discussion after the presentation and maybe during if you have questions, so feel free to break in. That's my personal blog, that's my Twitter. Feel free to get in touch. So I'll just tell you a little bit about myself. I got my PhD in policy analysis, which is kind of an applied branch of economics. And as such, a lot of my work focuses on applications. I got into data science because of kind of the breadth of technologies that are available and the breadth of applications that they have, and I'm really sort of focused on applying the latest methodologies that I can in the work that I do. So that's the corporate tech blog that I manage, and that's my personal blog. Feel free to look those up. I'll tell you a little bit about ThriveHive. We are actually a Boston-based marketing organization. We sell managed marketing services to small and mid-sized businesses. One of the main things that we sort of talk to our clients about is that we offer guided marketing solutions. A lot of the customers that we deal with, because they're small and mid-sized, they may not have a marketing team. If they have a marketing team, this is sort of one of their early forays into digital marketing. So they really look to us to give them guidance on what is the best sort of product to use, what kind of results they might expect, and also what kind of resources they should dedicate to it. And so that's what I'm going to be focusing on today, helping customers understand what is the right amount of spend to dedicate to a certain product, and sort of understanding what is the spend level, the resource level they can expect to spend on digital marketing services generally. So this is sort of an imagined conversation, but it's a conversation that comes up a lot with the sales team. A customer will come in, they will be new to the whole digital marketing services. They will be pretty familiar with the business that they do, but they won't know what is the best spend level or what is the best product for them to purchase. So here's an imagined exchange between Bob the salesperson and a cafe in the South End. South End in Boston is kind of a ritzy, fancy area. I don't know what the South End is here. So they come in, they want to run a display campaign, display advertising campaign, and they don't know exactly how much they should spend. Now, in a perfect world, every salesperson has had experience with this client, with this kind of region. They have an answer to this question ready. It's $1,300. Boom, done. But in the real world, and we live in the real world, fortunately for data scientists, a lot of salespeople don't have experience with all different regions, all different industries. So they need something to give them the information that they need to answer these questions. And that's where a sort of model-based approach, in my view, is particularly powerful when information sort of needs to be surfaced to the stakeholder in the business. And so if we're designing the perfect model, we might want to know exactly what is the right amount. We want a model that has the best accuracy, predicts exactly how much this customer is going to spend. But again, we're living in the real world. It's going to be very hard to design that model. And honestly, maybe that's not the model that we want to design, right? It's not a very good conversation starter to say you should spend exactly this amount of money. It's probably better to be like, here's the range that we see customers like you spending, and then the conversation can go from there. But beyond that, something that's useful for salespeople is to understand what type of customer they're dealing with. What is the budget level of that customer? Are they a very new business that is looking for just to spend the smallest amount to get the initial kind of digital marketing return? Or are they a bigger client that is just sort of dipping their toe in the water? So it might make sense to be like, well, you're thinking about the display advertising campaign, but why don't you think about some search engine marketing services that we can also offer. So the basic aim of the project is we want to not only be able to predict a realistic spend range based on our past data, we want to also use that data and other data sources to kind of estimate what is the budget that this customer has, which is, kind of ambitious and kind of a little bit beyond the scope of a lot of traditional machine learning projects, because we don't really have a ground truth in terms of what is the actual budget for this customer. So we're trying to use the spend information that we have and some other available information to get at a budget range. Yeah, and also another aim, and this is, I don't want to make this the third point, this is probably the major point, right, is actual implementation of this. Actually being able to go back to that conversation with Bob the salesperson and give them the information that they need based on the model that we've designed. So there's some similar work that has been done in this area. There is customer lifetime value prediction, which is basically over the lifetime of the customer, how much can we expect them to buy, for what amounts. A lot of the times those use probabilistic models, and I'll get into what is a probabilistic model and why is that useful. And then there's some work that I've seen called wallet estimation models, which is basically what I kind of just said, combining information that you have about spend and some information about the industry generally, and getting an idea of like what is the wallet size of the customer, how much more resources could they dedicate to, in this case, digital marketing services, but in the IBM research case, it was for the IBM enterprise services. So let's talk briefly about just what is a Bayesian model, what is a probabilistic model. It's sort of based on this idea of like Bayes' rule, which distills down to can we improve our prediction of the probability of an event based on observations, right? It sounds like a very simple, that's just sort of the simple like idea behind it. Of course, that's something we as data scientists think is kind of intuitive, and I think that's the power of a Bayesian model. It's a pretty intuitive way of thinking, right? We, as people, go through life, we make observations and we update our prior beliefs. And so that's sort of how Bayes' rule kind of works. I won't go too much into the equation here, but with the discrete event case, you're trying to say what is the probability of A happening being that given that I've observed B. And that can just be extended to the continuous case where what is the probability of a certain parameter given that I've observed X observations. So these have a lot of applications in marketing. It's not a new method to apply to a marketing context. A lot of the times estimating time to purchase is something that probabilistic models are used to sort of get an idea of there's a certain distribution of time between each customer's purchase. You can imagine a customer going into Amazon buying, I don't know, cat food or something like that. They might buy a big box of cat food and then, after a certain amount of time, they'll buy another box of cat food, and that's based on kind of a distribution that you can pre-specify. Also, there's models called media marketing mix, some arrangement of M's, that basically use these probabilistic models to understand the contribution of different marketing channels to an actual purchase event. And a lot of those times, those are using Bayesian models and actually using hierarchical Bayesian models, which we will talk about now. Just to give you like sort of a brief overview of what a hierarchical model, I don't know, did anyone go to Thomas Wickey's discussion yesterday, his talk yesterday? You can raise your hand if, like a couple of people. Okay, good, great. So I get to do it. So he did a really good job of explaining it. I actually used his blog. The link is right here. His blog is really good if you're interested in probabilistic modeling generally. But he had a sort of walkthrough of one of the canonical examples of what a hierarchical model is. The link is there. Let me tell you exactly what a hierarchical model is. It's basically, rather than estimating like a single like intercept or a single beta, a single parameter for an entire population, you're estimating sort of group level parameters, or you're allowing the parameters to sort of vary by these different groups. And that's the idea behind a hierarchical model. Typically, when it's actually called a hierarchical model, these levels sort of stack into each other. Another canonical example is students and teachers in a school system, and so estimating parameters for the school system, for the school itself, and then for the teacher is another sort of hierarchy. You can see how those things nest into each other. But generally that's the idea behind a hierarchical model, that you're estimating group level kind of parameters. And the canonical example that Thomas Wickey goes through in his blog is estimating the relationship between having a basement and radon levels across counties in, I think it was Minnesota. And so there's three different kind of strategies for doing that. The typical strategy is a pooled model, right? You estimate a single intercept, a single effect parameter across the whole population. And if you think about that, that will probably work, but it probably makes sense to account for some of these group level differences. You have a bunch of observations for whether the house has a basement or not and their radon level. Maybe you want to group that by county, right? Maybe you want to estimate something for each county. And maybe your approach to doing that is having a separate model for every single county. And that's called the fully unpooled model or the individual model. But you can also see how that's kind of problematic as well. That probably makes sense to share information across counties. Probably the relationship between having a basement and radon levels is like fairly similar, though it might vary to some degree by group. And so maybe it doesn't make sense to have an individual level model. So that's when we get to what is a hierarchical model or a partially pooled model, where basically you have one model and you're estimating a per county or per group intercept and effect. And just the Bayesian part on top of it just says that those parameters are drawn from a distribution. You can basically, if you just had a flat, the prior distribution, if you just had a flat prior on these parameters, it would just be a frequentist, kind of hierarchical or mixed model. Any thoughts or questions on that? Cool. I'll go on. So why even go this route, right? Intuitively, it kind of makes sense, right? Because there's differences by groups, and you want to kind of account for those differences. But what does that actually like shake out to in terms of like what your outcome is? In the case of the radon example, you're trying to estimate the relationship between having a basement and radon levels. And this is also from Thomas Wickie's blog. Here's three different counties from Minnesota. Each of the lines are basically a sample from that parameter before, that beta parameter that we had back here. And you can see the blue lines are the individual level model, where it's a separate model for each county, and the green line is the hierarchical model. And you can see the green line is kind of consistent. The relationship that it estimates is pretty much the same, right? Like having no basement is associated with lower radon levels. And it doesn't matter that the data is a little bit differently distributed by these counties, it's pretty consistent in what it's estimating. The individual level model, on the other hand, sometimes it seems like it shows no relationship, sometimes there's a negative relationship, it's a little bit more inconsistent, and it's more sensitive to things like outliers. So that's sort of the power of a hierarchical probabilistic model or a hierarchical model generally. In the Thrive Hive context, we similarly, just like the relationship across counties of having a basement and radon levels is probably has some shared properties. The relationship of different products and the spend levels is probably, there's some shared properties as well. There's a lot of people that are spending this kind of medium amount on each product. There's some people that spend a lot of money, and there's some people that spend very little money. And so that sort of distribution is probably shared, even though their locations or their means are a little bit different. So that's sort of the justification. I guess the other justification is I think these methods are cool, and so I wanted to try them out. So we're data scientists. Let's talk about data. Thrive has data for this project. We used about 9,000 customer marketing campaigns across 5 products since 2016, and the initial spend on these different products. I have the distribution there. I'll get into like what those products actually mean in 1 second. But the 2 groups that we focused on in this case were product and region, because we thought that those were probably pretty informative groups that we wanted to kind of like group things together into. We also had some covariates in terms of industry data and size data. So let me talk a little bit about the products. So on the right here, your left, here's the distributions of log spend across these 5 different products. This is a lot of detail about these different marketing campaigns, but the important thing that I want to talk about is what is the expectation that we have out of estimating the posteriors on these product level parameters. And the expectation that we have is typically, can you guys see that? I can barely see that. Typically, email and display marketing campaigns are on the lower spend level. They tend to be smaller businesses or businesses that are not very digitally invested. So their spends tend to be lower on that product. Things like search engine marketing tend to be larger companies, more sophisticated companies, and companies that are willing to spend a lot more on digital marketing services. And you can see that in the distribution here. So we'd expect that if we're going to estimate this model, that we're going to see a little bit of this pattern. Email and display sort of on the lower end, SEM on the higher end. Another thing that I'd point out is that SEO, which is search engine optimization, is a kind of fuzzy solution that sometimes it's a small company that like has no website or no capacity to build a website, and they kind of contract with our SEO providers to kind of create content for them. And sometimes they have a website, sometimes they're on the more sophisticated level, and they just go to us to kind of optimize like where they're appearing in search results. So a lot of times SEO has this like kind of wide distribution of possible spends. Any questions on the products that I'm displaying here? Cool. Okay, so let's get into some code. So we use PyMC3, which I highly advise, especially if you're very familiar with Python, because it has a very, I felt like, intuitive syntax for Python users. So basically this is you create the model context, and it's sort of as simple as just specifying your prior distributions and specifying your likelihood function. In this case, it's just a linear function of the different parameters and just sort of normally distributed. And you get this kind of nice DAG graph basically for free out of PyMC3 in the most recent version. So this model particularly is the pooled model. We're just estimating 1 alpha, 1 beta for all of the entire population. And again, we're estimating a distribution of alpha and betas because it's a probabilistic model. So that's the pooled model sort of as a baseline. Then there's 2 hierarchical models that we put in. So it's hierarchical with just product level alphas or product level intercepts. And so you can see here I just essentially replaced the intercept with product alphas. Is there anything else I wanted to point out about this? Yeah, so it's just you're specifying the product alphas as essentially a vector of normally distributed parameters. Another thing I should point out that these are unit Gaussian priors that I'm using, which are fairly uninformative and kind of a baseline prior that you might use. There's definitely a lot of discussion about whether it makes sense to use uninformative priors or not. I am not sophisticated enough to get into that discussion, but we can talk a little bit about what effect having a different prior might have on the model afterwards. So this is just an extension of the previous model. It's, again, another hierarchical model, but we just have another level where we have actually region intercepts here. So you can see that there's region alphas also included. Yeah, and so we can talk a little bit about what it would mean to have like a cross between product and region and effects that vary by these different groups afterwards. But this was sort of the first kind of baseline model that we wanted to put forward. So we have this model, right? And so how do we actually get to the posterior distribution for our parameters? And that comes from a sampling process. In this case, we're using MCMC, which breaks down into Markov chain Monte Carlo. Are people familiar with that process fairly? You can raise your hand if you're fairly familiar with that. I like a kind of mix. Okay. I won't go too into depth about it, but basically Markov chain is, the concept behind Markov chain is that each state is dependent on the previous state. And so you basically are sampling from this distribution, trying to find parameter values that increase the likelihood of the data, given that that is the parameter value. And so, it'll pick a step and it'll choose that step if it increases the likelihood. If it doesn't increase the likelihood with some chance, it will still accept that step just to allow it to explore the space a little bit more. And there's 2 methods for sort of executing these MC samples. One of them is the Metropolis Hastings, and I have kind of a visualization there. I also recommend that blog post. The blog post does a really good job of breaking down the different sampling techniques. And then there's Hamiltonian, which is more based, it's sort of based on like a physics kind of interpretation of how the sampler works. Basically, the sampler kind of travels across this probability space that you've defined. And it will sample more. You can sort of see, like, this is a visual like representation of it. You can sort of see that you can envision it as like a pit, right? So these are the high density, the lower parts of the high density, high density probability. And so when you put your sampler across it, it samples more from those lower spaces and less from those higher spaces. And it's just a more efficient and tends to be a little bit better at exploring a kind of complicated probability space than the Metropolis Hastings approach. And there's just an adaptation that's called no U-turn sampling that I ended up using for actually sampling from the posterior. So let's get into the sample of the posterior. So that's good background to have to be able to understand what PyMC3 kind of gets you in terms of visuals. That's the inference button that they talk about in their documentation. And you can see here on the right, this is sort of the trace from the sampler. This is the values that it's sort of sampled from. And typically you want to see something like this. Does this have a little, it does have it, oh cool. You typically want to see it to like sort of explore this space kind of back and forth, not get particularly stuck in one space or another space. I don't have an example of that, but you can look up on some blogs for like what it looks like when it's sort of failed its trace. But this is basically tracing all the values that it sampled, and then this is the distribution of those values. This is the posterior distribution that you were trying to get to in the beginning. And so I have the two models that I outlined before, just product level intercepts and then product and region intercepts. And you can see this is actually fairly reassuring. As I said, display and email you would expect to be on the lower end in terms of spend because there's typically lower spend for those products. And then SEM is at the higher level of spend. Now when you include region, how I interpret this is that there's really not a lot of variation by region, that including another parameter for region level differences is not really contributing much. It's essentially estimating the same value. So it may not help much to have this. And a good way to compare models, right? You try a couple of different models, you want to know which one is like probably the one that you want to move forward with. One metric that you might want to use is the widely available information criterion. It's similar to the AIC that you use in sort of non-probabilistic models, and that you want to have a lower number means that it's a better sort of fit to the data. But in this case, the lower value is not by that much. And again, by looking at this, it doesn't seem like having a bunch of those parameters really gets us much value. So it probably makes sense to just stick with this product level coefficients. Any thoughts, questions? Okay. So once you get this, right, we were talking about what we wanted out of this was a spend range. And what is the really nice thing about a probabilistic model is that sort of by design, you get a distribution of predictions rather than just a point estimate of predictions. You get like an actual distribution over the possible predicted values. And that comes from something called a posterior predictive distribution. And once you have that distribution, you can sort of sample from it, from whichever sort of value that you give it. So you have going back to that example, you have your cafe in the south end, and you want to sample all of the possible spends for a certain product. You can get that just out of that posterior predictive distribution. And it usually makes sense to actually look at your posterior predictive distribution versus your actual values to see if your model is completely off the wall, right? And so it might be a little bit hard for you to see here, but these lighter lines are samples for each of these different products, samples from the posterior predictive distribution of spend. You can sort of see it down here. The axes are the same of log spend. And you can sort of see that the distribution for email and display has this kind of bimodal shape, and that's likely because there's different sort of products and packages that we sell. And so there's probably a lot more concentration of density around those products that we're offering. So it's a little bit hard for where we specified sort of a normal distribution, for a normal distribution to fit a distribution that looks like that. But for SEM and SEO, which seem to have like a much more normal sort of shape, it seems to do a reasonably good job. And just a quick metric to actually add some numbers to that difference. We're not just looking at the visual differences. I just did a two-sided t-test of the average of a sample from the posterior predictive distribution and the actual distribution to see if the means are different. And you can see at a p of less than 0.05, they're not too different. That's not necessarily saying that this is the perfect model. We fit it in the perfect possible way, but it's to say that the model that we're using seems to work reasonably well at predicting the spend for customers based on the data that we've seen. So I also promised to talk about budget estimation, right? We have the spend model that works reasonably well, or we're somewhat satisfied with what it's outputting. Now let's talk about the actual budget estimation. And as I said, we don't have a ground truth here. We can't just, I mean, we could do a survey of our clients and ask them what their budget is. Whether they'd actually tell us that information is one thing, and it would just be costly to actually get that budget information. So we want to sort of get at kind of a synthetic ground truth that we're sort of synthesizing by a few different publicly available sources, and I have them up here. So basically, the idea is from the economic census, we're able to get payroll by state and industry level. And just from industry standards, we know that payroll is about 15 to 30% of the gross sales revenue. And then we have another source that goes from gross sales revenue to marketing budget. Again, these are a couple steps removed, but the idea is to get a realistic budget range. And just looking at the results of just this PyMC model based on that synthetic ground truth, the results were pretty okay based on our just running it past our sales team. But that's not enough, right? We want to actually combine it with the spend model that we already sort of created. And you know, this is still kind of in the experimental phase, so there's a couple approaches that we've tried so far. And one of them was to just translate the spend percentile into a budget percentile, right? So we get the distribution for a particular client, for a particular product of possible spends, and we see how that maps onto the actual percentile of spends total for that product. Then we just take that percentile and we map it onto, for the same industry and region, their budget range, and we get sort of a estimated budget for that particular customer. And that's sort of a simple way. It's kind of just translating from one distribution to another. It probably makes sense to combine the two distribution information that we have into a bivariate distribution. And in this case, it wasn't actually implemented in PyMC 3. I just used SciPy stats to create a bivariate distribution from the spend and region distribution. Oh, and also, this is not actually the distribution. This is just to visualize what a kind of bivariate distribution looks like. So here's the sort of results that we got out of it. I broke it down by product because that's what we've sort of been looking at so far. And you can see it kind of looks almost exactly the same as the posterior distributions that I sort of showed before, where display and email are kind of on this lower end, SEM is on this higher end. It's not particularly an exciting portrait, it just because basically what we were doing was mapping from one distribution onto the other. But we do get out of that, I would argue, a sort of realistic range that we could take and provide to the sales team. What happens out of the bivariate distribution is a little bit more of an interesting picture. Like SEO, like I said, has this like wider kind of distribution, and I kind of like that was the result of the bivariate estimation. But what is not probably right is this display and on target. We know that display advertising, as I said, tends to be from smaller businesses and businesses with smaller budgets. So that is probably is not right. That it would be in the middle of the realistic budget ranges. So all that to say, it's still a work in progress, right? It's a hard problem to solve, but I think this gives us some way forward. You know, with some actual customer data, if we're actually able to do a survey, we can probably combine what we have, maybe correct the synthetic ground truth that we have, and then try estimating again and see what we get. So another kind of exciting thing is, as I said before, one of our aims is to actually surface this information, right? It's really cool to like show a bunch of graphs, but the sales team doesn't care about a bunch of graphs, right? They don't care about posterior distributions typically. But what they do care about is being able to answer the question that I laid out before, right? Bob, the salesperson, is talking to this cafe in the South End, and he wants to be able to give them a confident, sort of realistic estimate of what their budget should be for a certain product. And so that's what we've sort of created. Is everyone familiar with Flask generally as a it's a way of creating kind of a web application out of in Python without having to be a web developer. I am not a web developer. And the idea is there's behind PyMC3 is Theano, right? Theano is back into PyMC3, and it has a function that's called shared variables, right? Which is a function that you can sort of plug in new variables into the kind of computational graph and then run that computational graph. And so that gives me the functionality that I need to create this web application, right? Input is a salesperson is talking to this cafe in this certain region. They put that request in. It replaces the shared variables. It samples from that posterior predictive distribution and gets like a distribution like this for each different product. Right here I just have SEM and social advertising, and you can see from like what I was saying before that SEM tends to be on the higher end, tends to have these wide distributions. Social tends to be on sort of concentrated around this lower end. And right now this is something that we have in production, right? Like this is something that we can serve up to salespeople whenever they have a question. They don't have the experience or necessary information to actually answer their customer's question about what is their anticipated spend level for a certain product. So that's pretty exciting and pretty cool for our sales team. So I wanted to talk a little bit about next steps, and maybe these could be even like sort of discussion points. But as I said, we don't have a ground truth for budget estimates, right? We are creating this synthetic ground truth, which may or may not map onto our actual population. So it'd be better to get some measurement of our actual population to improve the estimates that we have, but this sort of forms a groundwork on doing that sort of combining between the budget information and the spend information. So as I said before, the distributions of spends for the different products have that kind of bimodal distribution in certain areas, and that's probably because of the products that we're using. It probably makes sense to not just have these 5 arbitrary products, right? It probably makes sense to have products within those products that we have, right? So we sell in our SEO product, search engine optimization product, we sell one that's just sort of the essentials. It basically just makes sure that they have their keywords in order, make sure that they're ranking where they should be ranking. Then we have a more complicated package where they basically get their website content like kind of filled out for them. Those are 2 separate products and have 2 different spend levels. It probably makes sense to include that information into a model like this rather than just arbitrarily splitting it at these 5 groups. Like why 5 groups and not 20 groups, right? Having more informative priors, I talked about that a little bit. It seems like the spends are log-normally distributed. It's like fairly okay, except for those bimodal distributions, but there's probably more informative priors that we could apply to the model that we're using. Another thing that I talked about, we're just estimating these kind of intercepts, these group level intercept effects. We're not actually looking at the relationships, the actual betas that we're estimating, or we're not also looking at the crosses between region or location and products. Likely the SEM product is spend ranges are probably lower in certain locations than they are in other locations. That's something that we know for sure. So it probably makes sense to include a little bit of that into our model. And I'm talking about all of these things that we can just shove into our model, right? This is the dream world that we can make the model that just boils the entire universe. But it gets complicated, right? And just using PyMC3 and just using it on a single core on a single machine, sometimes the sampling takes a long time, sometimes it doesn't converge. Sometimes these models may not actually be a linear relationship that we're enforcing on the model. So in that case, it may make sense to start looking into some of the deep probabilistic modeling functions and libraries that are out there now. I just ran a very quick analysis using Edward, and Edward is a deep probabilistic library built on TensorFlow. I believe it actually is underlying the probabilistic module of TensorFlow. I'm not exactly sure of that. But what is amazing about Edward is it's fairly easy and intuitive to use, and that their tutorial materials and their documentation is just phenomenal, in my opinion. And so just by running through one of their kind of example out-of-the-box kind of models, I was able to come up with some estimates using a little bit more of a complicated model. And I just wanted to show you some of the early results. The distributions kind of look kind of similar, at least their ordering looks somewhat similar, and that SEM is at the higher end of the distribution. And display and email are sort of at this lower end. And that was just from a very simple kind of run through the capabilities of Edward. Yeah. So just to conclude, I guess I should conclude first. I think that these are pretty powerful methods. I think that it makes sense intuitively to take into account these group level differences, particularly if you have that group level structure in your data. I think probabilistic models are powerful when you're interested in looking at not just estimating sort of a point value for either your predictions or for your parameters. I think getting that picture is a useful thing generally. When you're looking at predictions, it may make sense to actually get a distribution of predictions rather than just the point estimate of it, particularly in this case where spend ranges was the target. The range was actually, the uncertainty level was the target of our model. And so if you have cases like that, if you have use cases like that, it might make sense to think about these probabilistic models. And as I said, following some of the materials that are available sort of free online, you can work with these models, and they're pretty accessible at this point, even though the title of my talk is less accessible. So I just wanted to thank the data science team at ThriveHive. This is all of us. I wanted to thank all of the open source contributors that make these things possible, ODSC for having me, and you guys for sticking around at 4 o'clock in the afternoon. Thanks. You guys have questions?
Why are you looking at, why are you looking at just on spend rather than the efficiency of the ad spend? I think if I was one of your customers, I wanted to get the most bang for my buck rather than knowing what other people spend.
Yeah, I mean yeah, that's a great point. So the question is, why not look at efficiency of spend rather than just spend generally? And to answer your question, we are sort of looking at both, right? This use case was just to sort of, I think it's a fairly simple ask to say to our data that is all this historical spend, what is this customer going to spend? So sort of a first stage of that, right? The next stage might be to actually estimate the returns that they get. And we have some models for doing that. At the moment, they're not sort of in the same kind of framework. But yeah, you're absolutely right. Like the tool that we're building is a more general tool that says, here's what you should spend, here's what we expect that you would get, right, at these different spend levels. But yeah, it's a good point and a good question.
A question regarding your uninformed price. Have you tried to use the prior and the prior? So
yeah, yes, we did. The results weren't that different, but it's a good point. Typically, so the question was, have you tried using a prior on your priors? And so I'm assuming you mean like actually having a prior distribution for the parameters that are going into the priors. So just to show what that might look like. So these I just sort of hard-coded. The mu is going to be 0 and the standard deviation is going to be 1. This could be like a normal prior for mu and maybe a half Cauchy prior for the standard deviation. So we tried it. The results were not too different, but you're totally right that it probably makes sense to pick from a distribution rather than just hard-code it at that location. Other questions, thoughts? Has anyone used this sort of stuff before? You can either raise your hand or talk about it, whichever you feel more comfortable doing. Yeah. If you want to talk about it.
It's weird this kind of structure, but in R, so we don't have the PyMC3. So something like, have you investigated like something like stan?
Stan, yeah.
That is available like in Python and R, or something like ILA, it's like integrity nested Laplace approximation. It's a way of getting your marginals in an approximate way, so it's known to be much faster.
Okay. Interesting. Yeah. Yeah, I tried using PyStan before, and it was a little bit more complicated. I find PyMC3 kind of intuitive from like a Python background, right? So, yeah. Cool. Well, if there's no more questions, thanks a lot.